Hey, good morning. All right, so today we are going to continue our study of heaps, and then this will allow us to revisit priority queues. And then what we're going to do after that is we're going to go over a couple of common heap interview type questions. But first I want to point out what my expectation from the pre-internship is this week. I've been getting a lot of emails already from the emailing the mentor to set up the time for the interview for next week. Please do that today. You should do it by 5 o'clock so that way you can catch them during the normal business hours and then they can get back to you as soon as possible. If they haven't bugged you by Monday or Tuesday of next week, reach out to me. I'll follow up with them. That tends to happen to 1 or 2 groups every year. I have to poke someone to kind of remind them to respond to you. I've also been getting their Google Drive requests fast and furiously as well. Create a Google Drive and then copy that email that you sent to your mentor and save it in there. And then save that drive with me and your TA, project manager, and your industry mentor. And you should also, by the end of the weekend, so Sunday night, come up with your 8 to 9 good questions. So I have a description of how to look up information and what constitutes a good question. I went over a little bit of that in Monday's lab. And you may have also noticed that I had a title in there for you. So we're going to build up what you can put on a resume to convey your data structure experience as actual experience. And so I call all of you pre-internship software engineers. So in my view, you've put in a lot of work. You've demonstrated it through several creativity challenges and labs your competency. And now I've made a quote, for lack of a better phrase, a job offer to all of you. And now what you're doing is you're going to be working through in this professional experience, but you're still going to be demonstrating the concepts you've learned in the data structures course. All right, so what I want to do is kind of build upon this idea of the max heap and show you some applications that we can use to build and apply and improve upon our heap sort algorithm. So some of the drawbacks that we had when we were using max heap sort, is that we had the element at the top of the heap and that was the maximum value. And if that's what we want, that's fine. The issue is in order to be able to access all of the other elements, we need to pop all the elements off of the heap. If we want it from smallest to largest, like we did in the demonstration, we had to put it into a stack and then remove all of those. The issue is, well, what if I want to be able to store the remaining results? So when I put these elements off there, I don't have to reverse them using a stack in order to get them. I always want to put them into an array. Well, one thing you do is you could use push front onto a linked list. You could also use standard vector to do @0, which pushes all the elements back. But I want to try another thing. We're going to make a minimum heap. And the idea of a minimum heap is has the same heap properties as a maximum heap, except instead of the value being bigger than the 2 elements, or greater than or equal to the 2 elements, it should be less than or equal to. So what ends up happening is the value that is the smallest in the heap is going to be at the top of the heap, which is also the first element in the dynamic array at any given moment. So from max heap to min heap, there are a lot of things that are the same. We have the same dynamic array, we have the same access front elements, and when we can start trickle up and trickle down, the public methods can be the same as well. We want to get the same range, but we can use inheritance and polymorphism to make it a simpler program to write. And so I made 3 virtual methods. We already met the rule of 3, and we have just trickle up and trickle down that I want to make inherit, but we also have to make a min heap version of the destructor in order for this to be successful. So in max heap, what I've done is just like we've done before, we've done private to protected. So let me bring this up here. So I haven't max heap. So in max heap, you can see that I changed the private to protected, and then I did virtual void for trickle up and trickle down. And if I go down here after everything else, you'll see that I have the virtual destructor that's required for inheritance and polymorphism. The base class's destructor must be virtual. But you'll notice that the copy constructor is the same, and the assignment operator is the same. And the reason why is because at the core, both a min heap and a max heap are just dynamic arrays. So if we're iterating through one dynamic array and pushing back the same element, if we have a dynamic array that meets the minimum heap property and we're pushing back, the copy dynamic array will also meet that minimum heap property. So we don't need to rewrite the copy constructor or the assignment operator in order to make this work. So for push, we're just pushing back onto the element and then trickling up. And here, we don't need to do a virtual because we're doing the exact same thing. We're just calling the virtual private method. So this is another example of why it's good to split up public and private methods when you're doing recursive work. Or if you're doing some part that doesn't need, that's common to both the base and derived class, but then you have a derived version that's different, you can separate them out using this approach. So this can improve the, you can reduce the amount of work that you need to do in order to write a derived class. The element at the top is the same. If it's empty, it's the same. And if it's pop, we would just call trickle down. So all of these are the same. We don't need to do virtual. In the min heap, it's the same idea, except what you're going to see. In fact, I can show you in the slide here. First, I just rewrite the destructor, and then I write the operator. But the operator is the same thing. I just want to print out the elements in the array. You'll also notice in the minimum heap that just like you've done in your assignments, we have class min heap public max heap template. Everything else for trickle up, I'm just flipping those greater than sign, the less than signs to greater than. So it's the exact same thing, except now I'm changing from less than to greater than, so that way I can make minimum heap and maximum heap. Does everybody see that? And furthermore, the only other changes that I've made are to access the heap array. Since the heap array is a member of the base class, we need to use this keyword when we're doing inheritance. So that way we can make a polymorphic trickle up method. Does that make sense, everybody? And likewise with trickle down, we just do all this keyword to access everything. And I flipped again from greater than to less than in these two cases as well. Other than that, it's the exact same code. So that makes the inheritance and polymorphism to make min heap really easy to write. So let me show you min heap. You'll see that while almost the code is almost all the same, we just make it less than and we access this keyword. For trickle up and trickle down, we have these two private methods. And then after this though, all we have for the public methods are the constructor, where I call a max heap constructor. I just have a min heap destructor. We meet the rule of 3 because the copy constructor and assignment operator that we inherit are the same. And then all we need to do is rewrite our friend operator. So instead of having to completely rewrite all of these other methods or copy and paste them, we can use inheritance and polymorphism to reduce the amount of work necessary. And so you should have been able to see that when you were building off your sorted dynamic array, sorted doubly linked list. One of the benefits is you didn't have to rewrite a deleted method, right? All you had to do is have an insert method rewritten. So hopefully you can see how that kind of thinking with inheritance and polymorphism is contributing to stronger computational thinking. So from here, for test min heap, first I want to go down to main, and then I'm going to show you the methods that I've written in order to make this work. So in main, what I've done is I've created a minimum heap that's templated to int. And then I have a bunch of elements that I've pushed onto the minimum heap. And then what I'm going to do here is I'm going to pop and print. So I have a push and print method, which is very similar to the push and print that I did in the previous lecture. And then I have a pop and print where I'm removing the element from the top, and we're going to print, and then you will see the remaining heap array when we're done. And then to test to make sure that we have genericity, I'm doing the same thing with characters. And then you'll see that I have all the elements, and then I pop them all off, and I continue to do that while the heap 2 is empty. So heap 2, aggregates the dynamic array and checks to see the number of elements. So we wrote that method earlier this semester. And now what we can do is we can go here. There's pop and print. So what I do is I get the element from the top, and then I pop from the min heap, and then I say I'm popping this value, and then we'll see the resulting value. Does everybody see that? And then in push and print, again, I've called by reference. And now we've just, all we've done is pass a pointer. And then I'm pushing onto the element, and then I push that element, and you'll see the the minimum heap at every single stage. So now what I would like to do is I'd like to run make test min heap. And we're going to see first that in that overloaded operator, I print the length, so the number of elements, as well as the heap at any given moment. And we'll see that at any given moment, the smallest element is at the top of the heap, which means that it's at the front of the dynamic array. And then when we remove them, we see 0, 1, 7, 21, 27, 33, 44, 81, and 99. So now what we've done is as we're popping them off, they are in smaller order. When I do the same thing with characters, we'll see that the smallest character is always at the front, and then when I pop them off, we get D, A, D, E, F, M, Q, and R. So let me check the chat. Does anybody have any questions before I continue? Yes. Heap sort is, okay, so I'm going to make a slight distinction on big O log of n. So heap sort is what we're going to call big O of n times log of k. And I'm going to describe what I mean by k in a little bit. So bear with me, and then once I get to that point, I'm going to follow back up with you and see if I've clarified. Does anybody have any other questions? Sorry, so let me quick through. If you want to see everything that I just discussed, they're available here in the slides. So now we're here, modifying priority queues. So now we have a maximum queue and a minimum queue where I have the element that I need at the top at any given moment. So now let's go back and revisit what you did in Creativity Challenge 5, and then try to implement a priority queue using these max and min heaps, and then compare and contrast the two different priority queues. So first what I'd like to do is I'd like to show you my solution for priority.h. So you will likely recognize this. We have a template, we have a class priority. I have an element that's templated, and I have an int weight. And what I've done here in this priority, so I have my priority constructor with the member initialization lists, destructor, and then I have the copy constructor and the assignment operator. And then here, I've done this the way that you needed to do it in your creativity challenge. I'm going to show you why flipping these back and forth was important. So here, although if it's greater than, now we're comparing the weights and returning that value. And then I have the overloaded operator where I'm printing the priority element and that weight. So now we have that type of priority queue where I can have the element and using a weight in order to come up with that type of priority. So now I want to show you is a priority queue class that I've constructed using a minimum heap. And all of the push and pop methods are now just going to access the methods in the minimum heap. So what I would like to do is I'm now going to show you the code that was represented on that slide. And I've included min heap. And here we have aggregated the minimum heap into this priority queue. And I keep track, just like we've done before with priority queues, of the maximum length and the queue size. And then I have push if queue size is less than maximum length. So now we're going all the way back to that same principle we used in static queues to make sure that in an event you're doing something with a small amount of memory, like an embedded system, then you don't want to exceed a maximum queue size. So then we push it onto the heap and we increment that value. With pop, we want to make sure that this value is greater than 0. So we decrement after popping. Calling the front, now we're just getting the element at the top of the heap. So before, what we did is we got the element at the front of the doubly linked list. In this case, it was a sorted doubly linked list. And then here, we get the maximum length. We have the size of the current queue. And then if queue size is equal to empty, it will just return queue size, return the Boolean. The other thing we could do is we could check empty on the min heap, but all that's really doing is checking to see if the dynamic array underneath. So here, what we're doing is we're ultimately boiling this back down to the comparison of doubly linked lists and dynamic arrays. So now what I want to do is I want to show you the code that I've written to test my priority queue. In this priority queue, I've done the exact same thing that I've shown you in the example for the creativity challenge. I have a priority queue that I have templated to priority standard string. And then each time what I do is I create the elements like so, just like in the example that you read. And then in the next set of code, I push all of these priorities onto here. So priority 1 is cheering and 5. And I push all of these elements onto the priority queue. And then what I do is I get the priority result. I print the element at the front of the priority queue. And then I pop it off the top. Pop it off the front of the priority queue, excuse me. So now what's going on underneath all of this is I have this min heap where the element at the front of a dynamic array is the smallest value, and then I pop them off at any given time. So just like before, when I run make PQ test, it's going to print out this in a ascending order. So what I want to do is I want to ask you a question. It's not just I'm going to ask you what will happen if I change it, but I want you to think in terms of kind of computational thinking. When we want to make either one of these choices. So the first thing I want to ask you is if I go to priorityqueue.h and I scroll up here, and all I do is I change this from a min heap to a max heap, what do you think is going to be the final result when I run the code? I'll bring this up so I can see the chat responses as well. So I've now changed this from a minimum heap to a maximum heap. When I run this code, what is going to print out? Yes, it's going to be inverted. Very good. So let me run make PQ test. And that's exactly what happens. We have it in the reverse order. So we can use a minimum heap for a priority queue where I want to make the elements smaller, and a maximum heap when I want the bigger elements at the top. So this is what's actually this is one of the things that's actually being done in the standard template library. Remember when I showed you a lab and we actually passed the comparison function to the sort method? In that particular case, it uses quick sort, but we wanted to actually show how the object is compared. You can do that when passing to a priority queue as well. You can say which one you want to be smaller, which one you want to be larger. Because the standard template library for the priority queue has both underneath. Does that make sense? So the question is, why would I want to do that? Why would I want to be able to do it in either order? Can anybody think of some scenarios and some of the things that you've been researching, whether it's in your creativity challenges or when you've been preparing for the pre-internship, anything you've encountered where it's important to have a smaller value be the priority or the higher value be the priority? Has anybody encountered anything like that? All of you did creativity, yeah, all of you did creativity challenge 5 and not one of you came across any priorities? The TAs might be having a bad week next week when they're grading. Emma, this is your opportunity to share your creativity. I'm not gonna come around and smack you with a stick. Yes. Yeah, situationally. Sure. Okay, so sure. So I'm going to repeat it so that everybody on the Zoom can hear what he was said. So in this creativity challenge, we are coming up with a set of priorities for severities in an emergency room. Right? So the question becomes, you have to think about it. You have to think. So my wife is a surgery technician, so I have a little bit. So there's a lot of what goes on to when you're trying to convey ideas to the people who are working in the hospital. Ultimately, you have to know the language they speak and make the code work back that way. So when I say we have a severity of 1, right? You have to know what it is that the doctors and the scrub techs and the surgery technicians and the nurses and everybody who's in that hospital, what they think here in their mind when that happens. So if a severity of 1 means low, then we'd want to use a maximum heap. Severity of 10, boom, we want that at the very top. If the hospital says severity of 1, and that's the language they use to convey the very worst thing, severity of 1, oh, that's like, you know, the worst thing we need to do. We need to get that done now. Then you'd want to use a minimum heap. So now you're using the data structure to speak their language. That's a good example. Does anybody have any other examples of things that they did in their creativity challenge? Please feel free to share. Yes. Sure. Okay. So in this creativity challenge, and forgive me, we all have masks, so I'm very bad with names. But the student said that we have this list of files, right? And we have several requests. All of us are trying to print things out. And what you've decided is that the person with the smallest file, which is the smallest amount of work, should be at the front because that will make things run faster. So we have one person with 1 page, you might have somebody with 2 pages, but has a big picture. That one might go a little further back because that one might take a little bit longer to do. So basically what we want to do is we want to try to get these out as fast as possible. So that's another really good example. So what I want to point out and kind of allude to things you're going to learn about in other courses is this idea of aging. So let's say I have a dissertation I'm trying to print. It's 300 pages long, and I got to print out 5 copies for my dissertation committee. So this is for those of you who are possibly thinking about grad school. I'm not trying to scare you that my dissertation is 300 pages long. But you know, if I have 1,500 pages I need to print on one of these big printers, and people are just constantly printing smaller things, the priority queue is going to put those elements towards the top, right? So at some point, there's a potential for something called starvation. And never mind. There's a potential for something called starvation where you never actually get to the bottom of the priority queue. So what you can do is I say after a certain number of elements, like a certain number of passes over, that aging begins to go up, right? And so the priority begins to go up. So we call that aging. So the longer you're in there, the higher your priority goes. So I'll give you an example. When I ran the algorithm to match the pre-turn ships, everybody who lost out on their first choice, their priority went up a little bit because you had been rejected from a choice. And so when I came across that next thing, you're more likely to get one of your next choices because you had lost out on a tiebreaker, right? So that's an example of using that, and priority queues are used to implement that. Does anybody else have any other thing that they did in their creativity challenge? I think it's interesting. It has an application here. A lot of shy students. Do we have anything in the chat? I don't see anything here either. Has anybody come across anything so far in their creativity, in their pre-internship research that might potentially have that? Okay, well, let me hide these meeting controls and put this back to the min heap. So there's all kinds of different opportunities to use priority queues in different ways. So now the other things that we have to consider about in terms of computational thinking is trade-offs. The one you did in Creativity Challenge 5 was a sorted doubly linked list. And it ultimately depends on how you sort it. Because it's fixed in the way that you sort, you would have to make the priority queue work to match, which is why in the Creativity Challenge, you had to flip those back and forth. Remember, you had the priority queue and I had it the opposite way. The reason I had it the opposite way is to match what's being done in the standard priority queue in the standard template library. So you flip them back, and so if you have 1, 3, 4, 6, and 7, then you get the minimum priority at the front. So the comparison of several elements, first let's talk about inserting into this priority queue. In a sorted doubly linked list, you have an average of n over 2. And so we say that's a big O of n. And for now, we're going to call the insertion into min heap log of n. So the insertion speed is a lot faster. And if you're inserting hundreds or thousands of elements into this priority queue, the obvious choice becomes the heap. Does that make sense? So, however, there's a drawback. In memory, we have to think about what's actually being stored in the priority queue. This is one of the examples of what I call data versus structure. So when we actually have, if we have just integers, and if it's a 64-bit integer, and then we have 64-bit pointers, this idea of the memory for a sorted doubly linked list seems prohibitive. It seems like the priority queue would be better because all we have is the dynamic array, which has twice, at worst case, twice as many elements in the dynamic array, right? But let's say that this element that we're putting in here is not just an integer. It's some sort of big class object. So the bigger the class objects get, the more that the nodes and data dominate. Does that make sense? So the larger the elements get, the better the sorted doubly linked list implementation becomes. So ultimately, what happens is, the bigger your elements are, the more you want to consider this with a trade-off of speed. More often than not, if you're trying to do things, speed is going to become your primary concern. But again, getting back to low memory application, if you're trying to store larger elements in a limited amount of memory, then a sorted doubly linked list priority queue would become beneficial. The other thing is, in a sorted doubly linked list, every single time, it's big O of 1 removal. And then we can guarantee that the next element after we pop front, it will be there every single time. With min heap, that becomes our best case, but we have this worst case log n because of our balancing mechanisms. I showed you that example when we had 81, 27, and 44, right? So even in this case, if we remove 81, we still have, now we have an unbalanced max heap because 44 needs to be in front of 27 in this case. So the goal is, with your understanding of data structures, this is where I went into this discussion of overcoming adversity, right? Something doesn't quite work out. Now you go back into your brain and go, well, wait a minute. I understand doubly linked lists. I understand dynamic arrays. I understand how min heaps work. I understand how priority queues work. We have a specific application where one approach doesn't quite work out the way we hoped. And we understand the reason that works because memory limitations, speed limitations, whatever one we want to choose. I know another way. And that's the benefit of understanding data structures in this context. There are different approaches to different problems based on your constraints. If you understand that, that's what truly makes one a computer scientist or a computer engineer. All right, let me check the chat before I continue. I don't see anything in there. Okay, so what I want to do for the remainder of lecture is I'm going to go over 2 common heap interview questions. I'm going to present my solutions and my approaches towards these problems. So the first one is called find the kth largest element in an unsorted array. So for those of you who come to my optional lectures, so Catherine, I'm going to pick on you because you just happen to be in the front. So what was the hint that I gave yesterday evening when you see this kth in any kind of leak code or interview question? What are they? What's the major hint that they're dropping to you there? If they use this term kth anywhere, they're dropping a massive hint that they want you to do some kind of heap. And this is what I'm going to show you why. So let's say I want to get the kth largest element in an unsorted array. And my initial approach, my brute force approach is, well, I know binary search trees. I even know balanced binary search trees. I know AVL trees. So when I just insert all of the elements in there, right? Then I have some sort of balanced tree. But then in order to get that worst case, that element, I then have to perform an in-order traversal to get the kth largest. Does that make sense? So there's some drawbacks. It's improved over trying to go through the dynamic array and then trying to keep track of everything. But all we need is k elements. If I have 1,000 integers, right, and I'm trying to find the 4th largest, all I need in the end is 4. Does that make sense? So this is why you're often going to see heaps referred to not just as big O of n, but that they can beat a big O of n log algorithm with a big O of n log k. And the difference is in the number of elements that the heap holds. So because we are getting some sort of element, we know if there are 5 elements in a minimum heap, that the element at the top is the minimum value and that the other 4 elements are in some sort of order, but they're bigger, right? Likewise, if I have a max heap, I know that I have the largest element at the top and that the other 4 elements are beneath it are smaller. So if I have a min heap, let's say I have 1, 3, 7, and 6, right? And I've put in 4 elements, and I know that these are the 4 largest elements when I've put in 4, right? Does that make sense so far? So if I come by and say, I'm going to put in the value 8, what I can do is I can just say, well, all I know is that I can get rid of that minimum value, right? And I can put in 8 to wherever it heapifies. Which means that now I have 3, we could say 3, 7, 6, 8, and then 8 would heapify up here, right? This means that I now have the 4 largest elements. One can go away. I don't care anymore. And in fact, no matter how many elements I put in, now I can guarantee that one will never be part of that solution. So all I need is the k largest elements to keep track at any given moment. So if I have 50 elements, I'm trying to find the 4th element. 5 elements has 4 largest elements. 17 elements has 4 largest elements. And 38 elements has 4 largest elements. So what we're doing is we're using the heap to do a kind of dynamic programming problem. So dynamic programming means I can go through and by using the minimum heap and saying, I only need to have the 4 biggest elements, and the moment I have a new largest, I pop that element off the top and then put a new element in there. I now can figure out the solution at any subset of those values. So that's why they say k largest elements. They're saying, we're going to give you some sort of constraint. I want to find those elements, and it doesn't matter how big it is. I just want to find that result. So that is why when they say k, I'm alluding very heavily to a heap. So let's say we have the first 6 elements, right? So this first 4 elements, 9, 17, 22, and 22. 9 is the smallest. So then I'm going to put in 55. Once I put in 55, there's no reason to keep 9 around. So why save it? We just pop it off. So there's the animation. So I'm going to show you the solution from 4 on to this set of insertions in 10. So the top 4 elements are 19, 77, 22, and 44. When I insert 55, now we have these 4. Now I'm going to insert 18. 18 is bigger than 17, so we've popped off 18. Sorry, we've popped off 17, and now 18 becomes the new element in the heap. 37 will result in 18 being popped off. Now we're going to put in 16. Well, 16 is smaller than the top of the minimum heap, right? So I just zoom right on by. We don't even put an element in. 43, and then 99. So now I have a solution for every single stage, k and greater. And because I only need to heapify the k elements, I've now significantly reduced the runtime of this particular approach. Does everybody see that? So let me first, before I show you the code and the solution, I want to check the chat. So the solution is to create a minimum heap. And once we have k elements, the kth smallest will be at the top of the heap. So we want to get the largest, the second largest, the third largest, fourth largest, down to the kth largest. And so anytime we beat the kth value, we pop it off and then push that next element on. And so at the end of the array, the top element will be the kth smallest element. I'm sorry, the kth largest. I apologize. And so getting back to, so Carson, this is the answer to your question that you asked earlier. So why is this big O of n log k instead of n log n? At most, we have to heapify k elements at any given moment. So even in a well-balanced tree, you still have to perform the in-order traversal, and you still have to keep track of every single element in the tree in order to know where that is. So if the more elements we get, the worse the binary search tree or AVL tree or red-black tree or B tree or splay tree becomes. So the heap will still only have 4 elements if k is equal to 4. So at the end, the solution will be at the top of the minimum heap. So first, what I want to do is in find kth largest. First, I'm going to scroll down to main. Yes, Carson. So I want to find the 8th largest element instead of 9. So if I make it a maximum heap, right? The issue is that the element at the top is the maximum element. And that's the only element I can access. Does that make sense? Yes. That's what we're doing. We're doing the minimum heap. That's the exact solution, is to do the minimum heap. So we only should pop off one in any given moment. So first what I want to do, and so let me walk through the code and you'll see how the solution goes. First, the only reason I wrote it this way with the void pointer is to just to do a review of the first week of the semester. So sometimes I do things like this. You go like, oh yeah, that's right, void pointers. Those are things that are real. So for here, I create a void array with 12 times size of int. And then if you recall, we cast the void pointer to integer pointer to tell the operating system to interpret those 32 bits as an integer. And then we put in parentheses and star to actually put in the exact value. And in this case, when I do inside the parentheses, when I do +1, the C++ compiler automatically interprets that as plus 32 bits, plus 8 bytes. So here what I do is I put in 12 elements into this integer array. And then to print everything else out, I go over again. I do with that iter. That's the exact same thing as if that was an integer array. I called it unsorted, and we use the array parentheses. So print out those unsorted values. And then I have a min heap. And then inside this function k largest, I'm going to pass the length of the array and the specific kth value I want to find. So we're actually going to perform this algorithm 12 times. So now what I'm going to do is I'm going to scroll up to the top where the final solution actually is, and I'll walk through it step by step. Now, if this was a dynamic array, I wouldn't have to pass int length because it has that private member inside that keeps track of the length. But since this is a void pointer, we have to pass that length. I think this might be especially helpful since many of you are in systems and you're starting to get familiar with C. This will really help you understand that procedural. So I'm hoping that helps you out in systems as well. So here, if kth is greater than the length, then I say kth exceeds the length of the array. So therefore, we just have to, it'll just print, it will not try to get the 9th largest element in a 4-length array. So here what I do is I then push all of the elements onto the heap. Okay, so that's for, okay, so I want to make sure I'm clear as to what I'm saying here. So the first thing I do is if I have 12 elements in the array, right? And let's say I have 5. So what this is going to do from line 16 to 18 is it's going to automatically put the first 5 elements onto the heap. And then what I'm going to do is I'm going to say from iter is equal to 5, iter is less than length. So now I'm going through the rest of the array. And now what I'm doing is I'm saying if this value, so here's that element that I'm evaluating, is greater than the element at the, then I'm going to pop off, and then I'm going to push that new value onto the heap. Does that make sense? And then from there, and this gets back, Carson, to your question, all I have to do is say, I'm going to grab that element at the top, and that is my solution. And so now let me run find kth largest. And now I'm running it for every single one. So I have an unsorted array, and I say the largest element is 1842, and then each time I run it, I get the result. So when I'm printing it out, it actually also produces a sorted values. Does everybody see that? Okay, so I don't see anything in the chat here. So there's all the code if you would like to review it later. Okay, last problem. So we'll do this for the last 6 minutes of lecture. First, does anybody have any questions before I continue? Yes. Only to review that we've done it in the past and to remind you that that's a thing. Furthermore, since you're starting to get, for those of you who are taking systems programming and you're starting to C is a very procedural language. So that's kind of a way of kind of reminding you that there's procedure, and hopefully that helps out with it. That was only a review, no other reason to do that. Hey, any other questions? All right, last thing, top K frequent elements. So basically you're given an array with a it can be an unsorted array, even though the example from LeetCode gives a sorted array here. Given a non-empty array of integers, return the K most frequent elements. So here I have 1, 1, 1, 2, 2, 3, 3. So I have the K equals 2. And so the elements that I want are 1 and 2 because 1 has 3 elements and 2 has 2 elements. So the way we have all the pieces put together to be able to solve it. So the first question, if I want to go through an array and get a list of the frequency, does anybody remember the algorithm we used to do that? We used the frequency in order to be able to get a sorted version. We called it a histogram, yes. We used the hash for that. Does anybody remember the name of the function? I mean, the name of the algorithm, but we did absolutely use the hash for that. Yes. Counting sort. You use a counting sort as well? Yeah, so absolutely right that we used a counting sort. So let me check the chat. Hash table, so Fangkong is absolutely right. And so that's what we did. We did a hash table. So now that now instead of emitting in order to do a counting sort, what we're going to do is we're going to use that heap to store the frequency. Then we can use that priority class and a min heap. So the priority can be the value of the integer, and the weight can be the number of elements. So just like the top K largest elements, if I have 10,000 elements in the array and I'm trying to get the 5th most frequent element, once I have this result, all I want to do is just get those top 5 most frequent elements and keep going in those and reduce the amount of time. But the thing with counting sort is that all we need is the histogram. So I can iterate through the hash table and just get the value. So what I want to do is I want to make sure that the element is not deleted or empty, and then use that try-catch approach. So remember when we used that try-catch, so I wrote that access of the value and we threw it. And the reason we threw it is because if you don't do that, the hash table will try to insert it automatically. And we saw that in the standard template library, I had 7 elements, but my maximum was 100. And as a result, we had 212 elements in the hash table, or 211. I apologize. That's the prime number. So here, all we're going to need is 19 hashes to do that, and we called that approach map reduction or map reduce. And so first thing I did is I made 2 modifications to the hash, to the linear probe, although I'm using a double hash to implement the solution. I returned a method getNumBuckets, which returns the size of the internal array. And then I have a method getKey, where I get in the location. And I go to that location, and if it's not active, I throw the exception. Otherwise, I return the key at that location. Does everybody see that? And then I do the other method that I did is I just did the same thing, but with value. So this allows me to get the key and the value, and then I can start putting those values into the priority queue. So for there, in my main program, I wrote a function called getHistogram, where I have a double hash, where I template the key, I template the key, and the value integer is the number of times we encounter it. And then I have the dynamic array of values, and they're both called by reference. And then just like before, I iterate through the dynamic array, and then if it contains that, I increment it. Otherwise, I insert that value into the hash and start with 1. And then what I do is I'm going to print out the hash afterwards. And then just like for this other crucial part, so this is what I'm going to go through, and this will be the conclusion of lecture. So a heapify, I've taken the double hash, a min heap, and an unsigned integer most frequent, and I'm going to go through and I'm going to apply that concept with the k most frequent elements. That if it's that we exceed that, and that's what goes on here, if I exceed that value and the temp priority is greater than heap top, then I pop it and then push the new value on. So we're applying that concept. And here I have try catch. So here's the try catch portion. In the last point, I have that temporary priority where it's count sort hash get key, count sort hash at I dot get value. And if it's empty or deleted, it just throws the exception and then we go to the next element in the loop. And just like before, we go up to most frequent, inserting them to make sure that we have at least that many elements. So let me compile it and then I will dismiss. And that is find k most frequent, right? Find k most frequent. And then I print out the heap. There's only 17 instead of 211, much better. And 9 was 5 most, 9 had 5 values, 100 had 4, 7 had 3, and 1 had 2. Okay. So if no one else has any other questions, I've gone 1 minute over and you are dismissed.